Hi there, everyone. So, before we continue discussing about energy, let's just recap what we have talked about before. So, what is energy? Well, it's something that we need to change the universe. So, whenever we want to change the disposition of something, we want to move something to one side or another, deform something, we need to apply energy. And how do we do that? By doing work. Right? So work is the ability to transfer energy. For you to transfer between different kinds of energies, you will need to apply some work, or sometimes work is going to be done. You may extract some energy because they release some process will release energy. For example, you might fuse atoms, you might fission them, and those processes they will release energy, and you can do work by using those energies. And also gravity, if you let something fall, the the weight, right, the force of gravity is actually exerting some work there. So we define work to be given by force times distance, right, times displacement. And this is actually not 100% true. For those of you who are more keen on maths, this is actually a dot product. And that is exactly why when we write this down, considering that those are actually vectors, we will then eventually have the cosine of the angle between them. So if this is a force, but the distance is only in this direction here, so this would be my displacement vector, then theta is the angle between them. So this dot product will then just give us, we would just take the the magnitude of the force, the magnitude of your displacement, and the cosine of the angle between them. So here they're not vectors anymore. Before you do the dot product, they're still vectors, but after, they're not vectors anymore. This is going to be a scalar, and work is a scalar. Now we have also defined the unit of joule, and basically 1 joule is the energy required when you move, when a force of 1 Newton, right, moves or acts through a distance of 1 meter. So it's quite simple to think of joule, if because you're just keeping your units, the standard that you should use, right, your SI units. So both newtons and meters are our standard units. So if you keep them, you will have energy in joules. Often we will have units, very very large units, like kilojoules and megajoules, gigajoules. Just remember, kilo 10 to the power 3, mega 10 to the power 6, and so forth. All of those are in your booklet, and you will have that available when you're doing your exams, when you're doing any practice, any mock exams. You will have them available, so you don't have to memorize them. However, I doubt that by the end of, I don't know, next year, if you study enough, you won't have those in your heart forever. Now, since we're discussing energy, a few important concepts are obviously the conservation of energy. And this basically states that the energy can never be lost, it can never be destroyed. You can only transfer between different kinds of energies. So your total energy in a system is not bound to change, right? It has to remain the same. So the change in energy would have to be zero in a system. Now, we also discussed quite briefly about force distance graphs. So let's say that y here is force and x is distance. And if we have a graph of how this force varies with the distance, this area here is a product of force and distance. And this equation is actually work. Now, usually shapes are going to be quite easy, at least while you're here at school. However, those of you who like maths a lot, you will eventually learn some mathematical tool called integration. And through integration, your curve might be very awkward, but you'll still be able to calculate quite easily the area under this graph. And it will also give you the work which was executed, which was exerted by this force here throughout this path. Also, in the last few minutes, we discussed some examples regarding power. And basically, power is energy over time. So not usually, not always we're going to be writing like that, so we can just say P equals E over T. Now, what if we replace this energy as work? So we know that energy, the transfer of energy, is work done, and work is given by force times distance. Remember that this is dot product, but I'm just now assuming that those are the magnitudes of the vectors and they are aligned, divided by time. Now, what is distance or displacement over time? That's velocity, or if it's just the absolute value, the speed. So if we're just talking about magnitudes, this would be force times your speed. And this is quite useful because it's basically another way for you to calculate power. So either if you have energy and time, you can calculate power, or if you have a force and a speed, you can also calculate your power. Now, getting to the new stuff. So I know that you have seen this before. You have all done the IGCSE or something similar, and you have discussed about kinetic energy before. However, I'll assume that you know nothing about it. So if you have any object of mass m and it's moving with a certain speed, and I'm just writing a vector v here, that's my velocity, the kinetic energy, which is usually denoted by ek or ke as kinetic energy, or here energy, what kind, kinetic, is the product of the mass and the speed squared divided by 2. Notice that here I'm taking the speed, not the velocity. Alright, and this is just the magnitude. So it's the square of the magnitude of this vector multiplied by the mass and divided by 2. Any object that moves will have kinetic energy. Now let me show you the proof of this equation. So let there be a mass, m, in space. Its initial speed is 0. And let's say that I start counting time at a certain moment, and I'm going to move this particle. So I move this particle some displacement or some distance s, and now in this new position I've applied some force for it to move, since its initial speed, its initial velocity was 0, and now since it was accelerated throughout this distance, there is some final velocity here, which is not equal to 0. And let's say that this time is capital T. Now the first thing that we're going to do here is use our Newton's second law. let's observe that the acceleration can be found by using that formula and rearranging, right? So if we rearrange, we'll see that the acceleration is force divided by mass. And it becomes very clear how mass is actually a property of something, of matter, that makes it difficult for it to change velocity. That's quite interesting. It's another way of looking at it. Now, the whole point of this is that I want to find some equation for work, and we are going to use force times distance. However, I want to find this distance, and we are actually able to find this distance just by using those values that we have here, and this results of Newton's second law, and we can also find this same speed in terms of all of those values here. So we will have to apply our Suvat equations. So the first one, let's try to find something for the speed. So take a look at this equation here, v equals u plus at. All of you have seen this one before, right? All of you have used it. Now let's just apply what we know. What are the conditions of this particular problem? So u here is 0, and we can use the result of Newton's second law for the acceleration here. And also, let's apply this for the second time, right? We're trying to find this final velocity, so time will be equal to capital T. So all of that will become force divided by mass, that's our acceleration, multiplied by capital T. That's our final speed. Now, another Suvat equation. We know that v squared, not that one, s is equal to ut plus at squared divided by 2. Now, we want to find the displacement, right? And we will have all the information that we need here. So u is 0, so this term will be 0. T here will be t squared, capital T squared. And a, acceleration, we can use Newton's second law again. So this will then become f divided by m times capital T squared over 2. Now we just have to go for our work equation, right? So work is force times displacement. Now in this problem here, displacement and the force, they are aligned, so the cosine between them is 1. So the product will just be, if I take the dot product between those two vectors, it's just going to be the product of their magnitudes. So force is, well, the force multiplied by displacement, which we have found here. So it's force again, t squared over 2m, right? Let's put a 2 here. There's just 2. Now notice that I will have some things here squared. So I have f squared, t squared, and I would not have m squared. And I would have a factor of 2 multiplying, right? So let's put this half up front. Half, then f squared, t squared over m. So let's say that I want to get all of those to be square. I will then have to multiply by m below and m on top. Since I multiplied on top and below by the same thing, numerator and denominator, I'm not changing anything, I'm multiplying by 1. The only thing that's going to change here is that I'll be able then to join this inside and get half. I'll just get this mass up front. So let's have m over 2. And what follows is ft over m. And I can just square all of them. Take a look, those two m's, they are together now inside of the square. And what is this here? What is Ft over m? That's our speed. So we may then rewrite this. This work done is our change in kinetic energy, and that is given by m over 2 times v squared, the speed squared. And that's the proof of our kinetic equation. Now, what about the gravitational potential energy? What is the proof for it? I know I've already shown you this one, but let's take a look at it again. So let's say that there's some mass here. I'm gonna call it mass m. And since it's on our planet, it's going to feel a force downwards because it has mass. That force is given by mg. So let's say that we let this go and it falls down. So this is another moment. The force, the vector, is still the same. I'm not really specifying if this charge was moving or if it was not, but the whole point here is the distance between those 2 points is some height h. I can and I will describe this as a vector pointing downwards. So what would be the work done by this force which we see here? So this force is actually pulling this mass down, so it's producing work, it's doing work. So this work is the force itself multiplied by the distance. So if we make this more specific to the problem that we have here, the force is mg, and s, the displacement, is simply our height. And that's basically it. Notice here though that since the force and our displacement vector, they're in the same direction, the cosine that would appear here, because this is, as I've told you before, this is a dot product. So since this is a dot product, you will in fact, those are 2 vectors, and you will in fact multiply those magnitudes and also multiply between the cosine by the cosine between them. But in this case, they are aligned, they are parallel, so the cosine here will be 1. So we only have to bother with the actual magnitudes of those vectors, which is basically usually the information which we already know. Now there's also another kind of energy which is very important, and it's the elastic energy, sometimes also called strain energy. And I would also like to show you the proof of how do we calculate this energy. And it's slightly different from the method that we have used for our gravitational potential energy and our kinetic energy. So for this one, we will have to remember how is the force extension graph, right? So if you all remember, when you have, let's say, a spring and a mass hanging from it, there will be some force, right? If you put more weight, then this force will become larger, so this spring will stretch more, right, if this mass here is larger. So I think all of you have seen similar things on the IGCSE, I guess. And one of the things that you discussed, and I would usually do some practical with you regarding this, just for you guys to remember. But basically, what happens here is we can plot a graph of the force and the displacement. So if there's no weight at the end of our spring, or if you assume, okay, that's my calibration weight, right? So you're gonna assume that this is displacement 0, and then from that point when your spring stretches and then you have a different frame of reference. So for example, from the top here of the block now to the top of the block right there, that's your extension. So you measure, basically you add more mass and you measure the extension, and you add more mass, you measure the extension, and then you plot a graph. And usually it's a nice straight line going through the origin, because those two are proportional. And not only are they proportional, but you also find that you can describe this using an equation, which is well known as Hooke's law. So the force is some constant multiplied by the extension. And this constant has several names, like spring constant, Hooke's constant, but it's most importantly the gradient of this line. So if you do rise over run, and you can see this using the equation, right? If you just rewrite this as k equals f over delta x, you can close here some triangle and calculate rise over run. That's exactly numerically the same thing. Now, when we discussed about work, I've told you that we can get something from the area of this graph. And actually, the area of this graph gives us the work done. Now, this is actually a very simple shape. We should be very capable to calculate the area of this shape here. So it's a basic triangle. The height here is f. Let's call this f. And this base here is delta x, the extension. So the area, therefore the work done, is the force times that extension divided by 2. Base times height divided by 2. But we know that force is k delta x. So we can replace our force here by k delta x, and since we're going to have delta x times delta x, that's delta x squared divided by 2. And this is the actual equation for our strain or elastic energy. And if you think about it, it's fairly simple to deduce, but not always, especially under pressure conditions, will we be able to deduce those. So all of those equations, you actually have them available, but I understand that part of the beauty of physics is showing you how things are deduced, how things are shown. Otherwise, you might just believe in anything, and that's exactly the contrary of how science works, right? I'm here to show you why those things work, and how, and all the maths behind it. That's the whole purpose of physics. That's why we use maths. Alright, so I think that's all for today, and I'll be showing you some more examples later on.